Okay guys, how's it going? We're going to be doing another video about kinetics. In this particular problem, we're going to be talking about second order reactions, which we have yet to encounter. Following that question, we're going to be talking about some plots and how if you were to, determine and have some experimental data, how you would figure out if your reaction was first, second, or zero order for that matter. So let's get started with number 6. The rate constant for a second order reaction shown below is 0.54 molar reciprocal molar at 300 degrees Celsius. So the rate constant is that K value that we were talking about before. So our K for this is going to be 0.54 reciprocal molar that we see. How many seconds would it take for the concentration of NO2 to decrease from 0.62 to 0.28? Well, it's going from something to another thing. So what I'm going to consider is that my A naught, my initial concentration, is going to be the larger of those two values, which is 0.62 molar. And it's going to another molarity, which is going to be my A at time t, and that's going to be 0.28 molar that we see. Okay. Now this particular question is asking us how many seconds would it take for the concentration to go from that to that? Well, because that's asking for time, we can write down the second order integrated rate law and solve for the variable that they're asking for. And since we've already determined the variables that are going to be used in this equation, it should be fairly easy to plug and chug and get this answer correct. So let's remember that the second order integrated rate law is 1 over my A at time t equals a positive slope, kt, plus 1 over A at time 0. We could solve for t by moving over 1 over A naught to the other side and dividing by k, and we can isolate t and plug in our values. So let's do that right away. So when we solve for t, you should get something that looks kind of like this. A naught over the value of k, and we have our time. Great. Let me move this over a bit so I have a little bit extra space. Okay, so now we can plug in our values. We have our equation, and all we do is to solve for t. So 1 over A naught, so it's going to be 1 over my A naught, or rather my A at time t, I said was the 0.28. We're going to be subtracting 1 over 0.62. Let me fix that. And my K constant for this question was 0.54, 0.54. And I can now solve for my t, and it's a fairly simple equation to solve now. So let's do that really quick. So we're going to set up a fraction, 1 over 0.28 over another fraction over 0.54. Cool, so let's figure that out. And our answer, so for time, well, let's take a look. What are my units for this? Well, it says seconds. So that means then, my answer here that I got was 3.626 seconds. Now let's double check and see if that's right. Occasionally, sometimes you have to add parentheses, so I'm going to see if parentheses make any difference. So I'm going to figure that out. Let's see if that changes the answer. Nope, we got the same answer. I got 3.626 seconds. Well, let's accommodate for the significant figures of this problem. It looks like we have 2, so then my answer, when adjusted, is 3.6 seconds. Great. And we solved for our time. So as you can see, these are fairly easy problems, as long as you can break down the question and realize the variables that they gave you. So a lot of the time, this particular chapter is of difficulty for many people because they can't interpret the question that's being asked of them. But I encourage you, like any other problem in chemistry, to break down the problem into the smaller segments that you understand, and hopefully you can rearrange it to something that is solvable. So that was our answer for the second order integrated rate law. So let's go to this next question, 45. You're given some experimental data of this particular reaction, and you have plotted the data points of the molarity changing with respect to time. And you have 3 plots. What is the order of the reaction with respect to A? And what is the initial concentration of A? Well, let's take a look. Well, remember, whenever we are doing any of these graphs, we want our slope for these to be linearized. And what I mean by that is all of these integrated rate laws, I can write them really quickly. Let's see if we can do that. So let's see. So the natural log of A naught, I'll give you just an example. One's negative kt plus the natural log of A naught. Well, this guy right here. Well, this particular equation has all of the components of a linear equation as well. So what I mean by that is that this natural log of A naught I can consider as my y, and the negative kt I can think of it as my mx, and my natural log of A naught I can think of as my b, my y-intercept. However, this particular equation has a negative slope, so it's going to be negative mx plus b. So this is kind of the trend with all of our integrated rate laws. They're linearized in such a way that if you were to plot the points using this rate law, you would get a linear graph. So what does that mean? So if you were to plot all of these points in Excel, for that matter, in with respect to different functions, like for example, if this first graph is a zero order graph that we see in the top left hand corner, because we haven't done anything to the value of A. It's just A over time. And this is kind of important because as a student, you're responsible for understanding how to interpret a graph in this particular section of kinetics. If the graph on the y-axis has just A that has not been tampered with, and the x-axis is time, that's your independent variable, then that's going to be a zero order reaction. If your y-axis is the natural log of A with respect to time, and that's going to be your x-axis is the time, then that's going to be a first order reaction. And then finally, if your y-axis is 1 over A with respect to time, and that's going to be a second order reaction. Now your job then is to determine which of these graphs is linear and which can be determined to be the order for it. So clearly 1 over A, the third graph in this particular problem, is linear. And the other two demonstrate some sort of curvature, which is not what we're looking for. So because of that, to answer this problem, what is the order of the reaction with respect to A? The answer is going to be second order, because we get a linearized graph when we plot the points. And what is the initial concentration of A? Well, that would be our starting point in the graph, which is going to be the bottom here, where we started with respect to time. So all we have to do is determine this guy right here. So that'd be our 20, or this would be 20 over here. So that's 1 over A. So let's say that's 1 over A. That's what our y is. And our value is equal to 20. So then to solve for just the initial concentration of A, all I would need to do is, multiply both sides by A. And if I do that, these cancel. And I'm left with, 1 is equal to 20 times the concentration of A. And that's not what I want. I want just to isolate A, so I divide both sides by 20. So 1 over 20 is equal to the concentration of A in the starting point. So 1 over 20, let's see what that is. 1 divided by 20. And yeah, that answer is going to be 0.05 molar. So you see, these graphs do provide a fair amount of information if you're willing to extrapolate it. And this last step in particular is of the most important, because given that we know that the graph is correct for it, we can use all of the algebra tools that we learned in previous classes, for example, the y-intercept and the slope, to determine so much in this equation. So what I would take from this is that the slope and the y-intercept represent very important parts of these equations. So to bring that up, so let's look at what the different parallels of this. So B, which represents my y-intercept here, B is analogous to the natural log of A initial. So that's what we had to do. We had to then solve for the y-intercept to figure out what my initial concentration was, which is what we just did right now. Now, what about my slope? My slope represents my rate constant here. That negative k is analogous to that negative m that we see here. And these are the different important values that we see. So again, I hope this was pretty helpful. This is a fairly common question that you can see on an exam, so you should be able to interpret all of the graphs and know what values or what units are on each axis and how you can determine, extrapolate data out of those questions. So again, I hope this was helpful. I encourage you to try more problems with this, of this style, because they really do stress your conceptual knowledge of what kinetics is and how the different rate orders work. So I hope that was helpful. I hope you have a good one, and we'll see you in the next one.